our last performer. Last presentation is Professor Mike LaChance from Department of Mathematics and Statistics. He's also Associate Dean in the College of Art, Sciences, and Letters, and he's going to talk about uncrushing the can.
Okay. So this is your favorite class. So this is a metaphorical introduction. I'm actually not going to crush a can, not on my head or anything like that. The metaphor that I want you to think about is when you have a can and you crush it, the top goes down on the bottom and the sides sort of crumple up, so it's the distribution of the crushing that we're interested in. This product, Z star AZ, is the product that keeps me up at night, early in the morning, if some of you know my emails. You can think of it as just multiplication. The A is actually like a table of numbers, a square table. The Z is like a column of numbers. They're complex numbers, but that doesn't bother us. This is as formal as I'm going to get, so the mathematicians in the room can see what the definition of the numerical range is. All you have to do is think about A, this matrix is like a boot. And the can is something the boot's going to crush, and the flat image is what we're going to pay attention to. So there are two things associated with a boot: its size and its tread pattern. So in the top three matrices, you can see there are different sizes, 2, 3, and 4, full treads. The other ones are sort of sparse treads, and those are the ones we get to focus on. When I talk about the can, I sort of misled you. It's not a cylindrical can, it's actually a spherical can. And the dimension of the spheres will actually rise with the size of the matrix. And so in order to sort of capture what higher dimensional spheres look like, timing, there it is. So you can imagine equally spaced points on a line and wrapping that around a circle. And you can imagine equally spaced points on a plane and wrapping that around a 3D sphere. And you can imagine equally spaced points in 3 dimensions wrapped around a 4-dimensional sphere. So this is the kind of imagery that we're going to be working with. When you think about what happens in terms of crushed cans, the little upper triangular 2x2 boot has an elliptical cross-section. When you look at this one to the right, you see this sort of tri-lobed affair. And if you look at the 4x4 one in the bottom, you can see is actually the little upper triangular repeated twice, and you see 2 ellipses. Well, what we want to do is focus on 2 examples today. We're going to look at a 2x2 boot. Effectively, it's a 3D sphere that's going to get crushed, and the profile of the crushing is an ellipse. And we want to understand what actually goes on. So in order to sort of figure this out, what we did is we took the images of circles on the sphere. Because they get squashed into a flat plane, we saw that the circles sort of overlapped, and it led to this sort of idea. Well, the idea that we saw is that each point in that shaded region is intersected by exactly 2 circles. Now, when I say we, who am I talking about? I have 3 colleagues who join me every Tuesday at 11 o'clock. We pioneered, I think, what we now call protected time. So we do not talk about restructuring of the college. We do not talk about our children. We do not talk about the weather. We talk about the numerical range. So what we did in this particular problem is we discovered that that little small loop on that sphere, that little loop gets projected onto the ellipse. That's the smallest little region. What surprised us is that the outside also gets projected onto that ellipse. We didn't expect that. In effect, it's a 2-to-1 map. So who cares about this? Well, the Math Monthly is it's a widely read mathematics journal. You don't use that phrase with math journals, widely read. Okay, so we're very pleased to have it there. You can see my collaborators there, Clifford Jabush and Viswanath. Our second problem, the one we're working on now, is what happens if you have a boot that has a diagonal tread pattern. Well, the crushing this time isn't into an ellipse, but actually into a line segment. And so what happens is we want to figure out what happens if we have a 2x2, a 3x3, and so on. So back to the 2-sphere, if we take equally spaced points and we crush them with this particular boot, we see that the points are not uniformly distributed. And so we make a little histogram, and then we simulate this and we say, how about if we had 2,000 points on the circle and we see this distinct pattern? And so we want to predict what that pattern is. Well, that's the goal. That's the gold standard of being able to say what that profile is. This is a well-known distribution. It's called the arcsine distribution. So we are just sort of establishing sort of groundwork. The next thing we want to do is turn our attention, though, to the 3x3 case. And so in the 3x3 case, we now have uniformly spaced points on a sphere. They, too, when crushed, do not distribute themselves uniformly. The histogram it doesn't tell very much with 90 points, but you start to see a distinct shape when you have more. And so the challenge for us is to say, what exactly is that profile? And we have been able to do this. So we can say what the little red curves are there for the PDF and the CDF. And that particular distribution is of interest, not necessarily to us, but it turns out John von Neumann in the early 1940s was trying to figure out what that distribution was and was unsuccessful. And it's still unresolved, so we at least have made a small mark on the problem. So now, flushed with success, we want to look at the 4x4 case. So once again, we see this sort of histogram, and as we increase the number of points in our simulation, we start to see, okay, this is the shape that we are trying to understand. And so this is, of course, a particular example. This is the same von Neumann type distribution that we're interested in. We do not know what the solution is to this yet. For the 3x3 case, we have two different approaches that yield the same result. We're trying those two different approaches here in this case. So that's sort of our work in progress. As I put together this last slide, I thought this whole thing that I do is sort of self-indulgent. I mean, it's like going down a rabbit hole, not to mix metaphors. Why would anybody do this? I'm gratified that it has some application to other people. But for my part, it really sort of feeds something inside. And that's why I do it.